Welcome to our deep dive into Stephen Hawking's A Brief History of Time.
Oh, a classic.
This book, it's a phenomenon.
It really is.
It's been translated into, dozens of languages.
Yeah.
And it's spent years on bestseller lists.
Absolutely.
More copies sold on physics than Madonna on, let's just say other topics.
That's true, and it really speaks to Hawking's ability to, to make complex ideas about the universe accessible and engaging for everyone.
That's exactly what we're aiming for today.
Right.
We're going to try and distill the essence of Hawking's exploration of the universe, its origins, its evolution, and the fundamental laws that govern it all.
Big questions.
Big questions indeed.
From the Big Bang to black holes, even the possibility of time travel.
Oh, we'll get there.
We'll get there.
Okay, so Hawking starts the book with this great anecdote about a scientist giving a lecture on astronomy, explaining how Earth orbits the sun and the sun orbits the center of the galaxy.
Pretty standard stuff.
You'd think so, right?
Yes.
But at the end of the lecture, a little old lady stands up and very confidently declares that's rubbish. The world is a flat plate on the back of a giant tortoise.
Oh, no, not the tortoise. It's always a tortoise.
What did the scientists say to that?
Well, being a bit smug, he asks, and what is the tortoise standing on?
I bet I know what's coming next.
Oh, you know it. She doesn't even miss a beat and says, "You're clever, young man. Very clever. But it's turtles all the way down."
It's such a funny image.
It is.
I think there's a deeper point here.
Definitely.
Right. We humans, we always crave explanations, even if they lead to an infinite chain of turtles.
That's it. That's it. It highlights how our models of the universe have evolved over time. We've gone from those simple, almost mythical ideas to these complex concepts we wrestle with today.
We've moved from assuming we're at the center of everything to understanding our place within a vast, dynamic universe.
Exactly, exactly.
And that shift in perspective is key, right?
It is.
Take Ptolemy's Earth-centric model, for example. It was the accepted model for centuries.
It's understandable why, it just seems intuitive.
Right. From our perspective on Earth,
Yeah.
It does look like everything revolves around us.
Absolutely.
But if it was so intuitive, why did people start questioning it?
Well, there were cracks in the model.
Like what?
Well, for one, it couldn't explain certain observations.
Okay.
Like why the moon sometimes appeared twice as big in the sky.
That's a good point.
Yeah, for that to be true, it'd have to be, twice as close at times.
Right.
Which would completely mess up the model's neat geometry.
So observations started to clash with the theory.
Exactly.
I bet that caused some tension, especially with the Catholic Church endorsing the Earth-centric view.
Oh, absolutely. The
Yeah.
Church, they saw Earth as the center of God's creation.
Right.
So the idea of a sun-centered universe was a direct challenge to their worldview.
I see. So Copernicus's heliocentric model, that was revolutionary.
Evolutionary.
But even then, it took a while to gain traction.
It did. It wasn't until nearly a century later with Kepler and Galileo that it really started to gain acceptance.
Oh, Galileo.
Yes,
He built his own telescope, right?
he did.
What an amazing commitment to science.
I know, right?
What observations did he make that really shook things up?
They were game-changing. He observed the moons of Jupiter,
Oh, wow.
4 celestial objects clearly orbiting another planet.
Not Earth?
Not Earth.
Wow, that must have been undeniable evidence against the Church's Earth-centered view.
Oh, this is a huge blow.
And then, to solidify the heliocentric model, we have Kepler.
Yes.
Refining Copernicus's work, he realized that planetary orbits weren't perfect circles, but ellipses.
A crucial insight.
And why was that?
Well, because it finally allowed predictions to match up with the actual observed motion of planets.
Oh, I see. So a combination of observation and mathematical modeling?
A powerful duo.
Yeah, a powerful duo in science.
Yeah.
But then things get really wild with Einstein.
Yeah.
Right. He completely revolutionized our understanding of space and time with his theory of relativity.
He blew everyone's minds by showing that time and space are not absolute, but relative.
Relative.
They depend on your frame of reference. And it all started with this seemingly simple observation about light.
Okay, hold on. What about light?
Well, scientists used to believe that light waves traveled through this medium called ether.
Ether.
Yeah, much like sound waves travel through air.
Okay.
And they even designed these elaborate experiments to try and detect this ether.
Oh, really?
Yeah, the most famous being the Michelson-Morley experiment.
Okay.
But here's the thing, they found nothing.
No ether.
No ether.
So what did that mean for their understanding of light?
They had it all wrong. Light doesn't need a medium to travel through. In fact, the speed of light is constant.
Constant.
Regardless of how fast you're moving.
Okay, that's kind of a puzzle.
It was a major puzzle. Until Einstein.
So how did Einstein solve this puzzle?
He had a very radical idea. Instead of trying to fit the observations to the existing understanding of space and time, he flipped the script.
He flipped the script, okay.
He accepted the constancy of the speed of light as a fundamental truth, and realized that our concepts of space and time had to be adjusted.
So rather than assuming light was behaving strangely, he questioned our assumptions about space and time.
Exactly.
That's
Exactly.
clever.
Right.
Where did that lead him?
It led him to the mind-blowing conclusion that space and time are not separate entities, but intertwined,
Intertwined?
forming a four-dimensional fabric called space-time.
Space-time.
And here's the kicker.
Okay.
This fabric of space-time, it's not static. It can be warped, it can be bent, and stretched by mass and energy.
Wait a minute, so you're saying that massive objects like stars and planets actually warp the fabric of space-time?
That's it.
Like putting a bowling ball on a trampoline.
Exactly. And this warping of space-time is what we experience as gravity.
So it's not a force acting at a distance? Like Newton thought,
No.
but the curvature of space-time itself.
The curvature itself.
So when you feel the pull of gravity, you're essentially feeling the curvature of space-time caused by the Earth's mass.
You got it.
Okay, that is seriously mind-bending.
It is.
But we're not just talking about some abstract mathematical concept,
Yeah.
but something we experience every day.
That's the beauty of it.
How do we know that this is actually true?
Well, his theory made a prediction
Okay.
that the gravity of a massive object,
Yeah.
like the sun,
Yeah.
should be strong enough to bend the path of light passing by it.
To bend light.
To bend light.
Wow.
And guess what?
What?
This bending of light was actually observed
When?
during a solar eclipse in 1919.
So they saw starlight bending around the sun.
They did.
That must have been a huge moment for Einstein.
Oh, absolutely pivotal.
And for science.
Of course, yes.
It confirmed a key aspect of general relativity.
It did.
But I'm sure it also opened up even more questions.
Oh, of course.
About the nature of space, time, gravity,
All the big ones.
and the evolution of the universe.
And that's what we'll pick up next time on our deep dive.
Can't wait.
It's going to be good.